Hello everyone. I'm going to make this talk in English, just so more people could see it on the internet. My name is Ilya Kibardin. I'm a computer vision engineer at X5 Retail Group and competition grandmaster at Kaggle. But today I'm going to tell you about not Kaggle competitions, but about two competitions on two different alternative platforms, about SpaceNet 5 competition and Tellus Ice Detection competition. Let's start with SpaceNet 5 competition. It took place at Topcoder, and the problem statement was like that. So given an image, a satellite image, you have to extract a graph of roads. You have to, your algorithm should output a graph with crossroads and other road connections as vertices and actual roads as edges. But just to output this graph, this was the problem statement of SpaceNet 3 competition that took place 2 years ago. But this year you had to also predict a travel time for each road. So you have to estimate the speed for each road. The metric used for the estimation of performance of the models is called average pathline similarity metric. It's quite a complex one, but in general it works like that. Your model outputs a graph. You merge the predicted graph into the ground truth one. Then you iterate over every pair of vertex and find shortest path in your graph between these two vertices. Then you compare this shortest path in the compound graph with the ground truth one. And your metric is just average inversed relative error of this length. When in SpaceNet 3 competition, when you just have to predict the graph, the length of the edges is just their like geometric length. But this year, the relative error is calculated over the predicted travel times for the roads. And organizers provided a great implementation of this metric on GitHub. On Python, just nice and clean 3,700 lines of code with such great programming best practices as copy pasting and debugging comments. So it was really hard to use. The dataset for the competition was gathered across 6 cities and totaled up to 5,000 image tiles. The tiles were square tiles with 400 meters each size, or 1,300 pixels. And the distribution of images across cities are not too uniform, so it was a good idea to sample the images in such a way so that neural network would see each city uniformly in order not to overfit on the more frequent cities. And also, all the cities are quite different. For example, we have Vegas with clean and with good road layout, so it's easy for the model to understand it, and it worked great on it. And Moscow with really complex road layout, which is really hard to estimate. So the difference between city mattered a lot, and it was really important to balance them. So let's move back a little bit to the SpaceNet 3 competition that was the 2 years old one. All the winning approaches then used this scheme. They trained a Unet model for segmentation problem of the roads. Then after stacking several models and thresholding them, you get a road mask. Then you run a classical computer vision algorithm called skeleton-ice. Now all your roads is 1 pixel width, and it's easy to convert them to a graph. And also it was important to run a series of post-processing on the final graph. I'm going to talk about it a little bit later. So this was the solution for SpaceNet 3 competition. Now we also need to estimate the travel times for each road. In order to do that, the organizers provided a baseline solution based on the winning approach of SpaceNet 3. In order to estimate the speed of the roads, they binned all the road speed into 7 bins and treated this as a multi-label segmentation problem. So in addition to just the binary mask of every road, you add several masks for every speed bin, totaling up to 7 bins for 65 miles per hour max. And then having this speed estimation from the bin prediction, it's quite obvious how you predict the travel time. So I started participating in the competition 7 days before the final deadline, so I haven't got much time. But I decided to start from the baseline solution. Then organizers provide a baseline solution. It's quite a good idea to start from that. By training and predicting just the provided baseline, you get around 0.44 score at the leaderboard. It's far from top, but it verifies that it is working. Then I improved the baseline pipeline just by replacing the model they use. The thing is that they use Unet with ResNet34 encoder. I improved that by replacing the ResNet34 encoder with the ResNet50 encoder. It has more layers, it is more precise, and most importantly, I used not the default torch-vision ResNet50, but the semi-supervised pre-trained model released by Facebook, which was pre-trained on image and billion images dataset parsed from Instagram by Facebook, and it is way more precise than the default ResNet50. And also I replaced the Unet decoder used in baseline with FPN decoder because when dealing with multi-class segmentation, the Unet decoder is too thin to get sufficient representation for multi-label segmentation. And the FPN decoder gets a richer feature of feature stack, and it's usually better for multi-class segmentation. That significantly improved the leaderboard score, but most importantly, when diving into the prediction and validation, I saw that the speed predictions looked way better now than in the original baseline. So I've decided, because I hadn't had much time, so that the speed prediction quality is sufficient enough to reach the high place, but the binary road segmentation is not too good, and I have to improve it. So I trained separate models for binary road segmentation. All my models used Unet decoder with heavy ImageNet pre-trained, and not actually ImageNet, but also semi-supervised pre-trained by Facebook, using heavy encoders like ResNext 101, and the training was carried out in 4 stages. 2 stages on smaller crops and 2 stages on bigger crops. Smaller crops allow model to converge better because you can use bigger batch sizes and train in really heavy model. And then you just fine-tune them using bigger crops. These 4 stages with progressive training on from smaller to bigger crop size provides better accuracy for the problem. I trained the model to optimize a weighted sum of focal loss and dice loss. These losses work great because the areas of road and negative pixels is quite unbalanced. And these losses deal great with class imbalance. And for every stage, I used Adam optimizer with default learning rate, reducing it every time the scoring validation stops improving. For image processing, I hope you can see anything. I used a standard set of augmentations during training, like shifts, rotates, scales, flips, random crop, of course, and also random shifts in hue saturation value image space worked great. And during validation inference, I carried out the predictions on the original full-size images, padding them a little bit with replicate padding to improve performance on image borders. Yeah, because all my models are fully convolutional, I don't need to crop or downscale my images during inference, and I can proceed with it on the full images. For all the processing, I used Augmentations library. It provides fast and really convenient augmentations for computer vision problems, and it's built by Kaggle masters, so I strongly recommend if anyone doesn't use it yet. So my final assemble looked like that. I was using 3 different architectures on 5 folds. The ensemble is not so big because the organizers, because this is a Docker competition, so you have to provide a Dockerized solution so that organizers could train them and reproduce your results. And it was required for the ensemble to be able to be trained in 48 hours on 4 Teslas. Also, during inference, I used default this time augmentation. That's the process when you from original image you create 8 new images by using every rotation on 90 degrees and flips. And then you average all these predictions with weighted mean, actually, in favor of more strong models of ResNext 100. Yeah. This ensemble gave me a much better score of 0.53 leaderboard, approaching me to the prizes places. And also one important aspect of my solution was improving of graph post-processing. So the original winning solution of SpaceNet 3 by Elbow, and so the provided baseline uses a series of post-processing policies for the predicted graph. For example, the first 2 of them is, the first is if the predicted vertices are closer than certain threshold, which is tuned using validation, you add an edge between them. Another policy is when you have 2 vertices far from each other with a bigger distance, but the angle between the roads is quite similar, you can also connect them. So this post-processing solves some basic problem in connectivity of predicted masks. But I added the third important policy to the post-processing, which works with 3-road crossroads, because the network seems to fail quite often on such crossroads. So for every vertex, we iterate above all other edges in the graph, and if the distance between them are lower than certain threshold, again using validation, we add an edge. We split the edge in 2 by adding a vertex to get connected with another road. And the final results are presented here. They were calculated above using 4 cities. The tricky thing here is that the score is strongly defined, like 60% of the score is defined by a score on the last city, Dar es Salaam. I hope I pronounced it right. This not only the city was not presented nor in training dataset nor in public test dataset. Nobody even know the name of the city until the final results were released. It was called like a mystery city or something. So such approach, of course, introduced quite a serious shakeup to the leaderboard, especially because this city is from Africa. It is really similar to another African city in the training dataset, but on the initial, when I showed the distribution of the images across the city, the only African city was the least presented one. So if you don't balance your sampling between the cities on training, you fail miserably on this new city. So that was a questionable decision by organizers by introducing such a mystery city, but still. And traditionally, all the SpaceNet winning solution are open sourced by the organizers on their GitHub. This one is not open sourced yet, but one should consider following the organizers' blog in order not to miss 5 great image segmentation pipelines when that comes out. And the final part I wanted to talk about in this competition is the topology loss for optimizing. The thing is that every traditional image segmentation loss, like F1 score here, or dice, or intersectional reunion, or binary cross entropy, any of this, that doesn't really correlate with the target metric. Because as you can see here, at the up in the middle, the F1 score is way lower than upright. But from the middle image, we get almost perfect road graph. And from the right, we lose the connectivity, so the road graph is awful. And the problem is that we are optimizing with backpropagation during training the traditional losses, which doesn't really care much about the connectivity and the form of road graph. So I tried implementing one of the proposed approaches called TopologyAware Laws. They propose a special loss term that is calculated like that. You make a forward pass of the image through a segmentation model, obtain a predicted mask. You take the ground truth mask, calculate the traditional binary cross entropy here, segmentation loss here, and save it for later. Then you use ImageNet pretrain VGG network. You make a forward pass through it using the predicted masks and ground truth masks. So then you take all the feature maps from the VGG for your predicted mask and for ground truth mask and calculate the L2 difference between them and call that a topological loss. And during training of neural network, you optimize the weighted sum of the classical segmentation loss and this topology loss. And the author claims that this approach gives a great improvement on such tasks as road segmentation, crack segmentation, or something like that. But I tried to implement it, but it didn't work great for me. So I dropped it, but it may be a good idea if you're working on a similar problem. Now, that's all for the SpaceNet 5 competition at Topcoder. Let's move to the second one I'm going to talk about. That's ice detection challenge at Japanese competition's website called SpaceNet. I'm talking about these competitions together because of the close deadlines of them, and you can having a good pipeline for image segmentation on SpaceNet, you could easily obtain the great results on this competition as well, just by replacing the input data. The problem statement of this competition was like that. You are given 80 big tiles of satellite images of sea with ice, and you have to find the ice regions on these images. And the evaluation metric is classical for image segmentation, it's just the intersectional reunion. I started participating in this competition like 5 days before the deadline, so I didn't have my time, and I approached it with the most straightforward baseline. I sliced the big images into overlapping tiles. It was quite important to look at the distribution of input pixels on the images, because the distribution of them of pixel values is really close to 0 and really skewed. So it was a good idea to train not on the original pixel values, but to preprocess them with logarithm and also some linear transform just to make them look better. And after slicing the dataset and using such preprocessing, I just ran the training pipeline from SpaceNet 5 I've talked earlier. And that doesn't work at all. So the intersection over union score is 0.70. This is far from top, because top solutions at this point had 85 score, something like that. But looking at this image, you can see that it is the resolution is obviously too high for the Unet to capture the necessary features for them, because it's like a typical image if the resolution is too high. So we just have to scale the images to be lower in order to so Unet could capture the necessary features. So we're just adding the downscale, 4 times downscale as the first step before the pipeline, and now that works. Also, this competition it wasn't Docker competition this time, so you just needed to submit a CSV file, or just submit the prediction. So I was able to get a nice ensemble here of 4 heavy encoders and 5 false for each. Also D4 test time augmentation for every tile, and that gives a score of 0.83, and which is close to the top already. But as I have said, I started competing 5 days before the deadline. When I managed to submit the ensemble, it was like another day before the deadline, and I was like top 5 or something, so I had to make like a final improvement in order to achieve prizes. But the competition just suddenly ended 20 hours before the deadline, and on the shake-up, I got the 2nd place. So. That's it. Also, funny fact is that all the prize winners are members of ODSI, so it was quite a nice rate on Signate competition website. So that's all for my talk. If you have any questions, I'd be happy to answer them.
Please ask your questions in English, because we have translation in this language, so it will be very helpful if you will ask in English. Yeah.
Thanks for your report. And what was the hardware used to train your models, and what was the time of training?
Could you please repeat the first one? What was what used?
Hardware. Hardware.
Okay. Let me remember. I used a lot of hardware for both of them because of the time constraints, and I had to make everything quick. But the SpaceNet 5 solution trains on 4 Teslas in 48 hours. And I've trained them on DGX hardware, so it also contains some Teslas. So that's quite an accurate estimate of the training time. I think that like 30 hours here I used to train the 2 folds of ResNet 100-to-1 because it's a really heavy model. And for the Signate competition, there were less data in that, so the model trained quite fast. I think that you can retrain the whole ensemble in like a couple of days on 8 Teslas V100 as well.
Any other questions? Thanks, Ilya.
Thank you.